Hello everyone. Today I'm delighted to present a paper published by our project team in IEEE Wireless Communication Letters, titled Channel Estimation for Stacked Intelligent Metasurface-Assisted Wireless Networks. I will divide the presentation into 5 parts: background, system model, channel estimation protocol, simulation results, conclusions. Firstly, multiple input, multiple output MIMO technology has been widely used in wireless communication systems. While it offers significant throughput gains, it inevitably increases hardware complexity and energy consumption. The emerging holographic MIMO HMIMO technology, leveraging a large number of radiating and sensing elements to concentrate energy in precise regions, has attracted our attention. Similar to MIMO, the extensive commands required for HMIMO may lead to high energy consumption and hardware costs. Therefore, a viable solution for achieving HMIMO is the use of metasurfaces composed of numerous low-cost passive reflecting elements. Although metasurface technology has proven capable of reshaping wireless communication environments and achieving low-cost electromagnetic response tuning, it still requires complex digital beamforming. To address this issue, we introduce a novel stacked intelligent metasurface SIM technology. Specifically, SIM consists of multiple layers of physically stacked metasurfaces, each equipped with a large number of tunable passive meta-items. It has an architecture similar to an artificial neural network, which can flexibly manipulate electromagnetic waves propagating at the speed of light and achieve HMIMO precoding and combination in the wave domain, significantly reducing hardware costs and energy consumption. To fully exploit the potential gains brought by SIM-assisted HMIMO systems, the accurate estimation of the channels becomes crucial. Given SIM's passive nature, it cannot effectively detect the channels of each meta-item and relies on assistance from the base station BS. Furthermore, in practical applications, the number of meta-items often far exceeds the number of antennas at the BS, leading to an increase in the dimension of the channel matrix and posing challenges for channel estimation in SIM-assisted HMIMO communication systems. Against this background, in this letter, we investigate the channel estimation in SIM-assisted multi-user HMIMO communication systems, as shown in Figure 1a. BS equipped with a uniform linear array, having M antennas serves K single antenna user equipments (UES). A SIM consists of L metasurface layers, each with N meta-items. By adjusting the electromagnetic properties of all the metasurface layers with an intelligent controller, the SIM can perform wave-based processing. Additionally, we assume that all metasurface layers have a square structure, and the metasurface centers are in the same horizontal line. Furthermore, all layers are parallel to each other, and the transmit antenna area is parallel to the SIM, as shown in Figure 1b. According to Figen's Fresnel principle, when the incident beam passes through a programmable meta-item in the first layer metasurface, the transmit wave will act as a secondary source and illuminate all programmable meta-items in the second layer metasurface. Therefore, the SIM-enabled wave-based beamforming matrix can be expressed as the cascading of propagational coefficients for each layer and the corresponding propagational channel matrix. Moreover, we assume a quasi-static flat fading channel model, i.e. the channel parameters within a coherent block are time invariant. The baseband equivalent channel from the last metasurface layer to the KCUE is denoted by HK, follows a complex Gauss distribution with mean 0 and variance beta k times r, where beta k denotes the distance-dependent pass-throughs between the last metasurface layer and the KCUE, R denotes the covariance matrix characterizing the spatial correlation between each meta-atom on the last metasurface layer. To address the underdetermined problem caused by the number of alpha chains being smaller than the number of meta-atoms in the last layer of SIM. In this letter, we propose an estimation protocol by collecting multiple copies of the pilot signals to probe the uplink channel. As shown in Figure 2, we consider side blocks, each containing tau p time slots. All the UEs send the same pilot sequence of length tau p over different blocks. Therefore, the signal received by the AMS antenna in this time slot of the phi block can be obtained, where WMH denotes the propagation channels from the first layer of SIM to the AMS antenna. PK is the pilot power, SKT is the pilot symbol, and NM-SIT is the noise. After collecting the signals received at the AMS antenna in the size block, we notice that it is necessary to suppress the multi-user interference in the received signals at the BS before performing channel estimation. To eliminate the interference between multiple UEs in each block, we adopt the mutually orthogonal pilot sequence strategy. After left multiplying the conjugate transpose of the pilot sequence transmitted by the case UE on both sides, and connecting the output signals associated to the M antennas, we obtain the measurement matrix for the case UE. Upon collecting the measured output signals over side blocks, the dimension of the measurement matrix becomes psi times m. The above underdetermined problem arises because the dimension of the measurement matrix is much lower than the dimension of the channel matrix n. Therefore, we only need to control psi times m is greater than or equal to n. To reduce the overhead of the pilot signals, we control psi to be the ceiling of n over m. After expanding the measurement matrix, we then focus on the estimation of Hk, and provide the expressions for the four proposed estimators. If the spatial correlation matrix R is known, we can use the MMSE estimator to suppress the noise. If the matrix R is unknown, the LS estimator can be used for channel estimation, but is very sensitive to the noise and its performance degrades in deep fading channels. To address this issue, we then propose two subspace-based channel estimators, which lack the amount of information about R while achieving better performance than the LS estimator. By replacing PRPH with its singular value decomposition SVD, we know that there is an asymptotic approximation in the MMSE estimator when the pK is large. Taking this into account, we obtain the RSLS estimator. However, it still relies on prior knowledge of the considered scattering environment. Then we consider an isotropic scattering environment. Similar to the RSLS estimator, the RSLS ISO can be obtained, where U2 is obtained by computing the SVD of PR ISO PH. Please refer to the bottom reference for detailed derivation of the above estimator. In summary, we progressively reduce the prior information required for channel estimation while still providing performance gains surpassing the LS estimator. Furthermore, after calculating the mean square error MSE of the proposed estimators, it is evident that the MSE of these four estimators highly depends on the transmission matrix P, which is closely related to the configuration of SIM. Therefore, we formulate the optimization problem for SIM configuration as follows, where the matrix P is the transmission matrix in multiple time slots. G psi is the B-forming matrix of the SIM in the size block. Phi psi L is the matrix of the transmission coefficients for the L's metasurface layer in the size block. and set n psi L is the phase shift of the nth meta item on the L's metasurface layer in the size block. To address this issue, we consider a codebook-based scheme to heuristically produce a suboptimal solution of the phase shifts. Specifically, for each estimator, we randomly generate multiple sets of phase shift vectors as the codebook and select the one that minimizes the corresponding MSE to configure the scheme during channel estimation. To validate our hypothesis, we conducted corresponding simulations. Here are some settings of our simulation parameters. As shown in Figure 3a, we discussed the relationship between the performance of the proposed estimators and the signal-to-noise SNR. With increasing SNR, the performance of all estimators improves, and the derived theoretical values accurately characterize the performance of the estimators. Additionally, in Figure 3b, by varying the number of UEs and sim layers, we observe that the proposed channel estimation protocol effectively mitigates interference among multiple UEs and can accurately estimate the channel for all setups. Moreover, as shown in Figure 3c, the NMSE of the proposed estimators is improved by increasing the number of meta items n, because the rank deficiency of the spatial correlation matrix is more significant as the number of meta items increase. Additionally, the performance of all proposed estimators degrades by increasing the number of antennas M due to constraints on the flexibility of matrix P resulting from fewer observation blocks. Also, we select the optimal P for each estimator from a random codebook of size 100 that minimizes the MSE of the four estimators. Compared to a random sim configuration, Figure 3D indicates that a well-optimized sim is capable of improving the NMSE for all the estimators. To sum up, in this letter, we propose four channel estimators for sim-assisted multi-user HMIMO communication systems. Channel estimation is, in fact, a crucial task for subsequent beamforming and signal processing in sim-assisted communication systems. To this end, we designed an effective channel estimation protocol to solve the undetermined problem where the number of antennas at the BS is smaller than the number of meta items on the last massive layer of the sim. Additionally, we derive the MSE of the proposed channel estimators and minimize them by appropriately adjusting the phase shifts of the sim. The following are some references for this letter. Thank you again for listening. Goodbye.